Okay, so for both of these problems, remember, anytime it asks you for a question that says what p-values can work, you typically need to do separately p equals 1 first, because that integral will involve logs, or natural logs. And then you can do p is not 1, and then those integrals will somehow always involve something like an integral of an x to the p, which is x to the p plus 1 over p plus 1, or something of that sort. There's two separate integrals that you have to take a look at. The big reason is when you integrate any of these guys, do you agree, oops, these are all the same type of integrals. Add 1 to the exponent and to divide. But the one that's totally different is the integral of 1 over x. Can you add 1 to the exponent and divide those? No, they go to ln's. So you have to look at two separate cases when you look at them. And the biggest thing is always trying to get that p to be powerful enough to pull the fraction down where that infinity is in the bottom. In both cases here, p has to be greater than 1. I didn't do the first one because I was able to watch a lot of you. This one, if you want to take a, well, I guess I should point. This one here, Daniel, can you see it? Because I'm pointing. This one here, I showed all of my work on that one here. Okay? Integration by parts. Okay? Guys okay with that? So let's dive into our section for today, 9.4, comparison tests. Okay, here we go. Comparison tests. There's two different types. As a little reminder, the tools you know so far. Geometric and telescoping series. Those, you know all about them. You know how they converge. And you can actually tell me what they converge to, which is really nice. The test for divergence is all for divergence. And on those, you're hoping it doesn't go to 0 because then it blows up. But if it goes to 0, you're like, uh-oh, I don't know what to do. So it's either converge or diverge, and then you have to go do another test. Yep. The sequence goes to 0. The terms, the dots, the measles on my snake. Okay? So if this doesn't go to 0, if this goes to 0, I have to do another test. So I taught you one, the integral test. But here's the issue with the integral test. Some integrals, you don't know how to take the integral. So if you don't know how to take the integral, you need another test. So I taught you the p-series yesterday. The p-series is really quick, it's really easy, but it's really rare. Because the only form the p-series is the sum of what? What's the key to the p-series? 1 over what? N to the p. I mean, that's it. That's what you're looking for, 1 over n to the p. And in that case, if p is greater than 1, what happens? And p is less than or equal to 1, diverge. It's a great test, but it's very rare because it's only a very specific case. So, uh-oh, I hope I have another tool. Well, you do. Okay? To preview that tool, let's take a look at these guys. These three, you have no idea how to do. Okay? You know how to do the left ones. Okay? Anything on the left you can do. One of them's geometric, one of them's the p-series, and one of them you can integrate on the left. But any of them on the right, you can't do. Okay? This guy here, you can't do because it's not the p-series. I don't know how to integrate it. It's not, who's more powerful, an n or a 2 to the n? Who do you think is more, 2 to the n? So that goes to 0, so it doesn't blow up. So I don't know what to do with that one. Okay. Likewise, this guy, what's the last term going to be? 0, so it doesn't necessarily blow up. I don't know how to integrate that because I don't have a 3n squared on top. It's not a p series. It's almost a p series, but do you see that stupid +1 in the bottom ruins that? So you don't know what to do with any of those. This guy here, what's the degree on top? Degree on bottom. Who wins? Bottom. So what's it go to? So it doesn't, the test for divergence doesn't help me. I don't know how to integrate that thing unless maybe a trig sub. Do you agree that's like a yucky trig sub? P series? No, doesn't look like P series at all. So you guys see there are many types of problems that you don't know how to do yet. What's up? Yeah, you probably could. So when I say on the integral test, maybe the second one you could do an integral by doing a sum of cubes and then hope that it works out like one of my challenge set problems. And then on this bottom one, you could probably do trig sub, but it's yucky. I want to teach you a quicker way to do them instead. You guys okay? I need to teach you more. The first one that I want to just give you a quick preview of is number 2. Okay? This is the whole premise of today. I am going to draw this one for you. Those are the dots, the measles of the sequence. And you agree, if I sum them up, I'm adding up all of the lengths of those. What else did I teach you yesterday? You could also interpret those lengths and attach them as a rope. Or you could do what? Do the Riemann sums, because the widths of every one of them is 1. Okay? Or if you wanted to, you could cap it with 1 over x cubed. You guys agree? And that's how the integral test works. And we all know by P series, this one, oh, that should have been. This one converges by P series. Do you guys agree? Okay. Now, what about this red one here? So this one right there, n cubed plus 1. Just in general, what's true about that graph? What's true about the graph 1 over x cubed plus 1? How does it compare to 1 over x cubed? Always smaller. Why? You're right. Why? Bigger on bottom. That plus 1, do you agree, makes the bottom bigger, which makes the fraction smaller. So whatever it looks like, it might look like that. You guys agree? We could look at the dots, or we could look at the rope, or if you want, you could look at the Riemann sum, or you could look at the integral. What's your gut instinct telling you? I haven't taught you the tool yet, but what's your gut instinct? Do you think that red guy, the 1 over x cubed plus 1, do you think he converges or diverges? Why? Go. Yep. Yep, so we just said this one converges. The green guy converges. Okay, do you see what he's saying? If green converges and I put something that's guaranteed smaller everywhere, shouldn't that thing also converge? So it's like if I give you a package and it's a nice gift, it doesn't blow up in your face. It's not an Acme. The joke's already through my head and I haven't even told it to you. Wile E. Coyote and like the Roadrunner and all those Elmer Fudd and Bugs Bunny, and I give Finn a package, and in that package I'm telling him it converges, so there's no blow-upping Acme bomb. But I also tell him, hey, but there's another package inside that package. Should he be worried? No, because if the package itself converges, if it doesn't blow up, do you agree inside that, anything inside that that's smaller should also not blow up? You guys okay with that? So what's our gut telling us on 2? converge because it is smaller than a dude we know converges. Because, okay, just that thought process. I haven't formally taught you the rule yet, but what's up? Then 1 over n cubed minus 1. Do you guys agree 1 over n cubed minus 1 would be right here? 1 over x cubed minus 1. Would it always be bigger because the bottom would always be smaller? Do I know for sure? Do you see that preview to my story? That one's bigger than this. This guy converges. So do you agree anything below this guy should converge? Anything above it does not mean it should diverge. It means it, I don't know yet. You guys see that? Because at some point there's going to be a border that everything below is good, everything above is bad. I don't know where that border is yet, and that's a preview to today. Okay, so here is a preview, and I think I already summed it up pretty well, so I won't erase this and redraw it. Okay. If I give you the green guy, okay, this is just like I drew on the last page. I give you the green guy, and you know for a fact that the green guy converges. So this is a fact. I'll write this. This is a fact that you know that the green guy converges. And I give you a red guy that is always smaller than the green guy. Well, if you know for a fact green guy is converging, then you know the red guy also has to converge because he's smaller than the green guy. That's what your gut was telling you, and that's this theorem. It's called the direct comparison test. Okay? Now, there's going to be another version that you could use. Could someone paint me a picture of what they think could happen if you have something where you know for sure it could maybe diverge? Story time. Go. No, don't give me examples. Give me a picture, visual picture. Okay? Cool. Did you hear that from her? Daniel, did you hear that? Do you want me to put the microphone by her again? Try it again.
Hi, Daniel. So 1 over x always diverges, so any line above that would also diverge because it's bigger.
Cool. So anything below a converger should what? Anything above a diverger should what? Diverge. So here's the other part of the story. Okay? So here we go. I have a red guy and a blue guy, and I'm telling you for a fact, the fact part is the blue guy blows up. That's my fact. And that's what we're talking about is the blue guy blows up. So Zella's example was 1 over x blows up. So if I can give you any guy that's bigger than the blow up, he also should blow up. Okay? So if you're bigger than a diverge, you blow up. If you're smaller than a converge, you converge. Okay? That's the whole visualness of the direct comparison test. The next page, I'll teach it to you formally in the calc world way. But I always, when I do these problems and when I start giving you examples of these problems, I always draw a quick picture because the visual helps me way more than trying to remember all the wording that the test gives you. You guys okay with that? Okay. Okay, so here it is. Direct comparison test is this. It's everything I told you, but it's all in words. Okay? If one guy converges, then the other guy converges as long as that guy's smaller. And then it flips it around, and it says if one guy blows up and the other guy is always bigger, then he also blows up. What I would do is I would always draw a picture and go, okay, if this guy converges and I have a guy below him, what does he do? Converge. So if that, then that. That's what the first one's saying. That's how I draw my picture to remember it. And then the other one is if diverge, then what do you know about this black guy? Then diverge. To me, the picture is way more understandable than the wording because they're using the same A and B's, and it's just I like the picture better. Okay? The key thing is for all of this, that has to be true. One guy always has to be smaller than the other guy, or one guy always has to be bigger than the other guy. You cannot do it. This is bad. If I give you this guy and let's say he converges, and I give you a guy like this, you have no idea. It's the majority of it in the converge world. But that little sliver right here is where I get really confused because that right there, just that little brief moment, possibly could have been in a blow-up world, like a black hole. Okay, and right now, this one still would probably converge based off my picture, but if it leaked out, could it leak out like this? Like into an asymptote or whatnot. So you need to make sure I'm capping it at all times to make it converge. You guys okay with that? Okay. So, just like some of the other tests, having this statement is important. So I wrote down on this some of the important things that you need to have for different tools. Okay? Integral tests. You guys know it better than me. That's why I keep asking you. What are the 3 conditions? Okay? So you need to make sure you verify those to use the integral test. And for this one here, what's the main condition I need? One guy always has to be less than or equal to the other guy. If you don't have it, you can't use that. You guys okay with that? You guys okay? Okay. So now let's look at a couple examples. Direct comparison test is pretty nice when, here's the hardest part about the direct comparison test. It's really nice to do as long as you can fit this. As long as you know which guy is for sure bigger or smaller than the other guy. Okay? So, if I have this example here, I look at this and go, I have no idea how to take the integral. Who wins, top or bottom? So what's it go to? 0. So does it guarantee diverge? Do you see how I'm doing the divergence test there? And you can't tell. So it's not, I don't know about divergence test. That doesn't help me. I don't know how to integrate it. It's not a p-series. Help. What's the core part to this problem? 1/3 to the n. So the core part is 1/3 to the n. Do you guys agree? The annoying part is the +2. So the core part is that. The annoying part is the +2. Let me ask you there. Who's bigger, black or green, always?
Green, because the denominator is bigger on black. So
You guys agree? It kind of takes a moment. It's almost backwards. Who's bigger on bottom? Black. So who's bigger overall? Green. Okay, so I want to look at this guy, and if I write him like this, you might go, oh, I know him. Okay, so let me ask you this. What does this guy do? Converge, why? By geometric, and what's R? R is less than 1. Yeah, it's 1/3. Okay, so then right away I'm going to a picture time. I'm going, okay, here's my picture. Here's the green guy that I have, and he converges. And you just told me that the black guy is always less than him. Is this a good picture to tell a story about? So what happens to the black guy? Converges as well. So you can say this converges by the direct comparison test with n equals 1 to infinity of 1 over 3 to the n, which converges by the geometric series. There's many ways to write it. I won't really care as long as you kind of detail for me. How do you know? I used the direct comparison test with who? That guy. Why does that guy work? Because he's geometric. Go see how we did that one. Okay. So now I'm going to do one probably that is a diverger. Okay. So let's take a look at this one. Okay. Who's the core part? This is how you kind of think through these problems. Who's the core? The core is 1 over that, which is 1 over n to the 1/2. Who's the annoying? The plus 2. Okay? So, 1 over n to the 1/2. Who's bigger? Which one? Green? Who's okay with that? So green's bigger. Okay. So, let's see what we got. What happens to green guy? N equals 1 to infinity. 1 over n to the 1/2 diverges by p series. Okay? So then right away, before you get giddy, this is where people make the mistake. You know what a lot of people already want to say? The other guy diverges. Because one diverges, so the other guy diverges. Okay? That's what people want to say. But before you do that, there's the green guy. He diverges. Here comes the black guy. He's there. Can I say it? No. So I'm left with right now going, oh no, I don't know still. I want another tool. Do you guys get the idea? Like this again, I'm slowly like kind of teaching you how to walk out through all these problems, but on each day I'm getting you stuck on a part where you need a new tool to do it. Do you guys see that? Because the direct comparison almost worked, but I would have needed this thing to be up here, and then I could say blow up. But since this guy's down low, I can't say it. You guys see that? So I need to teach you more. Okay? Before I teach you more, I want you to look at these and which ones work, which ones don't work. This is the most common mistakes done with students. So try these 4 out.